All right, we shall begin. The people that I have as not here in this classroom at this moment are Max, Tioni, Amelia, Russell, and Connor. All good? It's a lot of people. Good thing we had the quiz last class period. We're going to learn today about star classification. So these pictures here are called Hertzsprung-Russell diagrams. And nobody wants to say Hertzsprung-Russell. And so we just call them HR. What they do is they show luminosity. What is luminosity? What does it mean? It has to do with the absolute magnitude. It's telling us, go ahead, Gabby, you're starting. It's telling us actually the power that it's giving off. It tells us how much light per second it's giving off. See? So that's what we have on the vertical axis. On the horizontal axis, we have the temperature. And don't need to go over what temperature is. Some things to note about this. Now, we're going to go over it in detail, and we're going to start a little bit back. But notice the scale. What's the relationship between, let's start here. The relationship between 1 and 10 is a factor of, multiply 1 by what to get to 10? It's a basic lame question, okay? It's not a tricky, hard question. 1 multiplied by what is 10? 10, right. So then if I go from 10 to 10 to the second, 10 to the first to 10 to the second, how much do I multiply it by? 10. Each one of these numbers is 10 times greater than the one below it. We call such a scale a logarithmic scale rather than a linear scale. It doesn't go 1, 2, 3, 4, 5. It goes 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4, 10 to the 5. So that means the difference between these two numbers here is between 100,000 and a million is 900,000. The difference between these two numbers here, between 1 and 10, is 9. So at the top, the differences are much smaller for the same size, or much bigger for the same size of thing on the graph. It's not linear. If you look at the horizontal axis, notice that hot is on the left side, cool is on the right side. And once again, the space between 20,000 and 30,000, so that's a difference of 10,000, is about the same as the difference between 3,000 and 5,000, which is only 2,000.
Well, that's what I thought you said the nebula's a red giant.
Okay, it's a blue giant. You're right. I don't know what I said, but it's a blue giant. That's not what I'm focusing on. I'm focusing on that the temperature scale is also not linear. It's also logarithmic. So this graph is a log-log graph if you want to have the name for it. What it's doing is classifying stars by putting, here's its temperature, here's its luminosity, boom, there it is on the graph. And you see that the stars tend to fall in certain locations. So that's what we're going to be learning about today. That's our basic goal today, is to understand that. So let's get started. Question left over from last class period. When is light from an eclipsing binary the faintest? So you have to think about what is an eclipsing binary and what's going to make it so you have the least amount of light coming from it. This one's going out long distance to absent. Tioni. What'd you say?
B and D are the same.
B and D are the same? Oh, well, there's a typo. When the hotter star is in front, when the larger, this is supposed to be when the smaller. Thank you for the correction. I feel ashamed. All right. Then the answers we doing really well. The answers we have 0, 5, 1, 2. So we're going to Tioni. And Tioni, I'm going to lead you through this actually. What is an eclipsing binary?
I just remember one of your pictures, like diagram you had. I picked C for this because I just went off one of the slides you had.
What happens when there's a solar eclipse?
Okay. I'm glad that I'm leading you through it, Tioni. What's a binary?
When the bigger object was in front of the smaller object.
Well, it's when two stars are orbiting each other. Binary, two stars.
Oh, okay, yeah.
So a binary is two stars, and eclipsing is exactly what you said. Eclipsing is when one passes in front of the other. So we have options here. We're going to have two stars, an eclipsing binary. At some point, we'll have one star here and one star here. Based on the colors, which one of these is the hot star? The blue one, okay? So at this point, we're going to have the light coming from both stars. But when they eclipse, we might have, let's say the blue one's the bigger one. So here's the blue one in back and the red one in front. Or we can compare that to here's the red one in back and the blue one in front. In which case am I seeing more light there? Okay, I should back up steps. I'm leading you through. If I have the same surface area, which is going to give off more light from that surface area? The red one that's cool or the blue one that's hot? The blue one, because the luminosity is proportional temperature raised to the fourth power. So the blue one's giving off much more light than the red one. So in these two situations, which one gives off more light? The blue, that'd be the upper one or the lower one? Okay, this one's going to be more light because you're seeing the same area in these two cases, but you're seeing all of the hot one here, not seeing the cool one. Now we could reverse this. What if the sizes are opposite? So what if we have, here's the big red one with the little blue one in front, or the little blue one with the big red one in front. Which of these am I going to get more light from? The one with the blue in front is absolutely right. It's more light because it's the same total area, but some of it is hotter. Excuse me. Well, the question was comparing these four situations. When the hotter star is in front, or when the cooler star is in front, or when the larger is in front, or when the smaller is in front. And so if we look at these, in the two situations, both of the ones that said more light had what in common? The hotter one was in front. It didn't matter if it was the larger one in front. Here, the larger one was in front and it was less light. Okay, yeah, you can see that. Here, the larger one was in front and it was less light. Here, the larger one was in front and it was more light. So it wasn't about the size. It was about the hot one being in front. So the correct answer was... Wah, wah. Oh, faintest. Okay, well, if it's the faintest, then we should probably check this out. I can pretend that never happened. So when is it the faintest? Well, it's going to be when the cooler one is in front. Hooray, because that's what most people answer.
Maybe I didn't understand.
And once again, I should reiterate, read the questions carefully, especially to me. All right. Here's the Stefan Boltzmann law that tells us about how much light is given off by a star. This right here is the equation for the surface area of a star. So what we saw before was something, well, it depends on how specific I was. There is the most specific you can get for this. The luminosity is that Stefan Boltzmann constant sigma multiplied by the emissivity. That's a number that tells us how efficiently it gives off light. 0 would be no efficiency whatsoever. 1 would be perfect efficiency. We call this black body radiation because blacks are perfect. They're 1 for the emissivity. And of course, if it's silver, it's 0 for the emissivity. Put those together, you've got silver and black, and you have the open radiation.
I'm down for the tape.
A is the area that's emitting the light, and T is the temperature of that surface. For stars, the emissivity is equal to 1. And so that's why it's not shown in the equation above, because it's just equal to 1. Stars are perfect black bodies, perfect emitters of light. So if we have a larger star, because that radius is bigger, it's going to give off more light. If we have a hotter star, because the temperature is bigger, it gives off more light. And so that's going to be important when we're looking at the luminosity of a star. That luminosity depends on the radius and the temperature. I've already talked enough about this. Here's the layout of a survey of stars in the sky. And the features you should note are there's a clear path here. It starts to spread out here. But we have most of the stars, in fact, 90% of all stars fall in that range that I've marked with the green. Because 90% of all stars are in that range that I marked with the green, we call it the main sequence. It's where most stars are. As we'll see, it turns out that's because that main sequence is where stars are when they are living their lives as a normal star. When they are dying, they grow. And so everything that's above there, so everything that is in this region here is dying stars. D-Y-I-N-G, right? Those are dying stars up there. And what's this down at the bottom? Anybody know what it is down there at the bottom? These are dead. These are no longer stars. Just the opposite. There's no gas. They're white dwarfs. And white dwarfs are what I call the bones of a dead star. You can have white dwarfs, you can have neutron stars, you can have black holes. Those are the bones of a dead star. And so that's dead stars down there. Well, how do we get all of this classification? I just told you a bunch of things about this, but we want to learn how this works. So it makes sense in our heads, and it's not just, well, he told me it's there, so I paid attention. Now, on a quiz next week, you're going to have to reproduce an HR diagram. You're going to have the axes right. You're going to have where the main sequence is and where the different types of stars are. So you do have to do some memorization here. But I want you to understand why as well, because we're physicists. Why is big in physics. So first, if you look here now, we've got some names. See a star here with the name Gliese? It says Gliese 876. I don't know if there's like a whole bunch of Gliese stars, but the Earth-like planets that you hear them finding are around a star named Gliese, which I assume is that one. Question?
Why do I go off so high?
I'll talk about it. We need to get through some stuff to get there, but I'll talk about it. It makes sense.
Yeah, they found one near Foxborough Centauri.
So here we can see some stars, and we see the sun. What's the temperature of the sun? About 5,800 kelvins. What is its spectral class?
Isn't that G?
It's a G2. Since the spectral class is based on the temperature, you can use the spectral class or the temperature for that horizontal axis, right? So we have on the left, O, remember our order that you do have to have that memorized too. O, B, A, fine gal, kiss me like this. There's no like this on this graph, is there? L's and T's are over here. And there's no stars. That's because, well, I said those have been added later, and T's really, they're in an in-between state. Question?
So is the sun more closer to a red giant than a yellow giant? I mean, a blue giant?
It is not a giant.
But is it more closer to like the temperature wise?
Well, its temperature is the same temperature as a yellow giant.
Yeah, just wondering, like, is our temperature more closer towards a red star than a blue star?
Yeah, we're in the middle. We're mid-range. You know, the color of the sun is pretty close to white. It's our atmosphere that makes it look more yellowish.
I'm just going to go outside and stare at it real quick to make sure what you're saying, right?
I'm going to recommend against that. In fact, I'm going to go on record as saying don't do that.
It's overcast.
As you know, he did say to do that. You all did that, right?
This is recorded.
He has a camera recording him.
Okay, so staying with the lecture here. So we can identify the temperature by this graph for the sun. And what about its luminosity? Well, the luminosity is in terms of solar luminosities. The sun is exactly as bright as one sun. See how that works? And so it's right there on the one line. And so you can look at this graph and you can say, oh, well, here's Sirius A. Sirius A is about 10 times brighter than the sun. That's 10 times more luminous. Doesn't appear 10 times brighter from Earth now, does it? Because we're way closer to the Earth than to that. And Sirius A is much hotter. It's a spectral class right there on the border between A and B because my line is not very straight. So you can see how each star, you know, its parameters for temperature and spectral class and luminosity by looking at this graph. We can determine the radius of the star by looking at this graph. It doesn't have radius on the axes. It has the temperature and the luminosity. But because the luminosity depends on the radius and the temperature, we can solve for the radius as a function of temperature and luminosity. So any point on the graph, I can choose, you know, this point right here, okay, Polaris. And if I find its temperature, once again, perfectly straight line, and I find its luminosity, and I put those numbers in, then I can know exactly what its radius is. And because of the log nature, the fact that both axes are logged variables, it turns out that constant radii form straight lines. So these green lines are constant radii. So you see down here the white dwarfs. The white dwarfs all have a radius of about 1/100th the radius of the sun. All about the same size. They're different temperatures and different luminosities, but the same radius. We look here and we see as we go up that the radius is getting bigger as we go to the hotter stars. What was your question, Gabby?
What's the Greek letter again? Not the pi box. Oh, looking for
Where are you talking about?
oh, next to T is it? Or-
Oh, here. Okay, this.
I don't know.
You gotta move on.
Oh, that, yeah.
Because you can't see through me? Is that what you're saying? Okay, that sigma is the Stefan Boltzmann constant. So it is a constant. It's not a variable. So in most of our calculations, we don't worry about it because we're looking at how things compare, and it's not changing. So you can determine the radius on the HR diagram by knowing the temperature and the luminosity that's given. Which brings us to our next clicker question. Which statement is true about temperature on an HR diagram?
Goodness.
Yoni, Yari, Russell, Jessica. All right, we're all in. 00611. There we have it. So I'm going to come back to this. I'm not going to ask anyone right now, but the answer we had was it's on the horizontal axis, high temperature to the left. Next question. Which statement is true about radius on an HR diagram? It's all up to you, Latifah. It's all up to you. Okay. This time around, we had 1, 0, 2, 3, 0, 2. Now, here is the graph again, the HR diagram. Where is temperature? It's which axis? Okay. Temperature is the horizontal axis. And where's hot? That was the most common answer. So we had 5 people, I think, out of 9 that got it right. Where is radius on this? The radius we can only get by calculation from the variables, or by looking, the radius increases as you go in that direction. But the radius is not on an axis. It can be determined from the graph, but it's not one of the axes. That one you had a much bigger time with. The correct answer, bigger time, harder time. The correct answer was it can be determined, but it's not one of the axes. That's what he said.
Mm-hmm. Can we see the zip for the vagina too?
Huh?
Since the beginning of class, you've been able to use it.
I don't remember saying that Deneb's a red giant, but that doesn't mean I didn't.
Use it when we were going through the list of giants.
Well,
Or the lab.
You even said that while we were out the other day.
the fact that, you sure?
Yes. Yes.
Sure you're not thinking about Aldebaran,
No.
You also
Doobie.
said Aldebaran, but you did say Deneb.
Antares,
You
Doobie?
said these, but you also said Deneb.
While we're at it, Capella, Beetlejuice. I don't remember saying that Deneb is a red giant, but a guy makes mistakes, right? Could have done it.
Wasn't Doobie also a red giant?
Yes.
Okay, she's not up there.
Yeah, just not listed here. So, more things about this diagram. We're going to get into the types of stars and what a red giant is in a few minutes here. Masses, we saw that temperatures increased as we went up the main sequence. Measurements of star masses, which is done by looking at things orbiting around them, shows us that the masses increase as you go up the main sequence as well. So you have the most massive up here at the top, and the least massive down here. But if you look at the white dwarfs mass could be anywhere between about 0.5 to 1.4 solar masses, and they could be anywhere in that white dwarf range with any of those masses. There's no connection between its position and its mass. And if we look up at the stars above the main sequence, you see those masses, they range between, he says, 1 to 20 solar masses. But you can have a star that has a 1 solar mass or 20 solar mass in a similar region. So there's more going on with the stars that aren't on the main sequence. The ones that are in the main sequence follow a pretty nice organized pattern. In fact, we're going to spend a lot of our time just understanding main sequence because it's where stars spend 90% of their time. I think this is the last thing of the HR diagram. If you take the main sequence star, so just looking at the stars that are on the main sequence here now, not sure what happened. If we take those stars and we plot their luminosity versus their mass, it's pretty close to a straight line on a log-log graph. Once again, this is not a linear graph, it's a log-log graph. And when you find the slope, you find that the luminosity is proportional to mass to the 3.5 power. Now, this leads us to one real quick and easy conclusion. If it's more luminous, what does that tell you about the energy per second that it is giving off?
It's giving up more.
It's giving off more. So the more massive the star, the more energy it gives off. By a pretty big factor. And of course, where does that energy come from?
If it's in the main sequence.
Yes, if it's in the main sequence. That's a very important caveat. Where does that energy come from?
The fusion reaction.
Fusion of hydrogen into helium. And so the mass that makes up the star is itself the fuel. And so I can calculate real quickly, since the luminosity is equal to the energy per time that's being emitted, but the energy is proportional to the mass of the star, because its mass is the fuel that it's using for that fusion, then that means I should be able to solve this for time. The lifetime of a star should equal its energy divided by the luminosity, which means it's proportional to the mass of the star divided by its luminosity. Using this equation, so what we find is the lifetime of a star is proportional to its mass raised to the minus 2.5 power. So if I have a star that is 1 solar mass, its lifetime is 1 solar lifetime. So I could say time for the sun is proportional to the mass of the sun raised to the 2.5 power. Minus, thank you. And now I can go to any other star and say the time for some other star is proportional to its mass to the minus 2.5 power. And if I divide these, actually I'm going to divide it the other way. So time for this star divided by time for the sun is going to be equal. Because of the proportionality, I can replace it with the equal when I divide them. Now, what did I do in that that last step? What did I do? I went from a minus sign to a plus sign and inverted which one was on top. And so what we get from this is the lifetime for any star is equal to the lifetime of the sun multiplied by the mass of the sun over the mass of that star raised to the 2.5 power. Or as we usually write this, the lifetime of the sun has been calculated to be 10 to the 10th years divided by the mass of that star to the 2.5 power, where the mass is in units of solar masses. And so we can determine how long a star will be on the main sequence. This was only a main sequence calculation because that luminosity relationship was only on the main sequence. But the main sequence life of a star is going to be 10 billion years divided by its mass in solar masses raised to the 2.5 power. So if a star has, we looked at, was it Polaris that had a mass that was about 10 times the mass?
Polaris isn't on the main sequence.
That was not the mass. It was the luminosity was about 10 times.
Polaris isn't on the main sequence.
And you're right, it's not. So it wasn't Polaris either. It was, what I'm thinking of was probably Sirius, but let's just take here. I think if I read this right, that Altair has a mass that's about 2 solar masses. So if I take Altair's mass and I put it into this equation, the lifetime for Altair is equal to 10 to the 10th years divided by 2 raised to the 2.5 power. Well, that's 2 squared is 4 times the square root of 2, which is 1.4. Anybody know that? 1.4 times 2 would be, or times 4, 5.6. It comes up often in photography.
I've never done photography. You know that? Whose camera is that?
You are a funny man. So we can calculate the lifetime for Altair because we know its mass is twice the mass of the sun. And if it's 10 to the 10th divided by 5.6, is that a longer lifetime or shorter lifetime than our sun's? Shorter. It's, about 1/6 the lifetime of our sun. Somewhere in the ballpark of, 1.8 million years.
Isn't it nice that the sun has a 10 billion year lifespan? So it's easy to measure the things with it.
Yes, but of course that's 10 billion plus or minus 1 billion, I think. It's not exact.
Doesn't matter.
Okay, so that luminosity tells us things about the lifetimes of stars. So it's really useful to know. Now the luminosity classes. We have broken up other regions on the HR diagram by what's going on. And so we have the main sequence there that is nicely colored. You see the colors red at the bottom right. Why is it red at the bottom right for the main sequence? Because they're cooler. Cooler stars are more red. Everything on the right edge is red. So if you go up above that, you see it's red for the giants that are in the same range. The main sequence winds up and gets hotter. Up to the right, all of those we call giants. So everything that's above the main sequence is called giant. Why? Because the largest radius is out here. Remember I said the radii are increasing as you go like that. So your constant radii are lines that look something like this. And so these are the biggest ones out here. So you see Betelgeuse is a really, really big star. And you come down and you see, here's Aldebaran. Very hard to read there. But Aldebaran is a pretty big star, but not nearly as big as Betelgeuse. And you keep coming down and you have are our Lyrae right there. Still much bigger than the sun, but much smaller than the other giants. And of course, the highest on the main sequence are bigger stars than the lowest. The names have symbols given to them, and these are called luminosity classes. So Roman numeral 1 is supergiant. That's a bad color. And it's broken up into two types, 1A and 1B. 1A is bright supergiants. And 1B is just your regular old supergiant. And then Roman numeral 2 is bright giant. Roman numeral 3 is just your regular old giant. Roman numeral 4, that's not how you put a 4, is a subgiant. And Roman numeral 5 is main sequence. So those are the luminosity classes. Why are they luminosity classes? Well, because in general, the lower the number, the more luminous it is. But that is only a generality. So what luminosity class does the sun belong to? It's a 5. So if we specify the sun, we can specify it completely by giving it its spectral type and its luminosity class. Spectral type, G2. Luminosity class, 5. So nobody wants to say G25, so we say G2V. And that tells us, the G2 tells us the temperature, and the V tells us, Roman numeral 5, that it is a main sequence star. So when you look at stars, you can classify them right away, okay? If it's a G, it's mid-range temperature. What temperature would a red star have for the spectral class? Oh, if you find out, kiss me. Which ones? K and M. K's and M's are going to be red. So if it's a K or an M, it's going to be red. Now, if it's going to be a red giant, what does its Roman numeral have to be? Has to be what?
What is a giant? Whatever giant.
1 or 2.
Anything that's not 5 is a giant. A subgiant is still a giant. Supergiant is still a giant. So a red giant is either, kiss me, K or an M, and then a Roman numeral that's less than 5. So KM1, KM2, KM3, KM4, those are all red giants. You can find a KM1, that's going to be a super, super, super bright star.
Will Betelgeuse count as that?
Betelgeuse is actually, yeah, it is a KMI. The Betelgeuse you see is up here in the 1As. And actually, Antares is also. So these right there, those are going to be really, really bright red giants.
Rigel's pretty bright.
But Rigel is not red.
Yeah.
Rigel is, I don't see it. Oh, here it is, there. It's a supergiant, but it ain't red. I don't. Yeah, here's just the listing of those spectral classes. I just wrote them on the preceding page, so there's nothing new to be seen here. How are these classified? How do we decide that it's a giant? One way would clearly be to look at where it is on this diagram, right? But there's another way, and that other way, okay, I don't have it here. The other way is looking at the spectral lines. Now let's think about what information do we get from spectral lines? Tell me things that we can learn from spectral lines. Did you say something, Aaron? What information can we tell about a star by looking at the spectral lines, the absorption lines we see in its atmosphere? It's really important. It's a huge amount of information we get from these. That's why I want to. Well, in some regards, yes. And in fact, that's where I'm going in the end part of this. But it's only in some regards, so I'll leave it until we get to the end. Things we've already studied.
You said never said whether like the walls were hot.
I haven't yet. You're right. What can we tell from those spectral lines?
The heat emission?
It doesn't tell us the heat emission. That we get from how, well, we get that from how much we see coming from it for the most part. It also would be, if we can determine its size and its temperature, we can get that. But I appreciate you taking a shot. Daniel, what do you think? Okay, well, here's the first thing that we learned. We learned that it tells us the composition. Because each type of atom has a unique set of spectral lines. We can determine the composition, at least in the photosphere, and the atmosphere above the photosphere of a star, by its spectral lines. You guys remember that? Okay. Another one it tells us about is motion. How can we get motion from that? How do spectral lines tell us anything about the motion? What happens if something's coming toward you? The spectral lines are going to be shifted toward the blue. We have a Doppler shift if it's coming toward you. If it's going away from you, the spectral lines are going to be shifted toward the red. And so we can tell if it's approaching or moving away. We can tell the speed of approach, or I'm just going to say moving away. We call that the radial speed. We tell how fast it's moving toward or away from us. And as we will learn in the near future, if we can determine how fast it's moving toward or away from us, it actually is a proxy that allows us to determine how far away it is as well. Other things we might be able to determine from that. Think back to Wednesday. I do. Because it's named after Woden. Woden's Day. Truly. And I'm just a weirdo. What did we talk about from the spectral lines on Wednesday? Which, of course, is not the correct pronunciation.
I don't know. I'm still not over Thursday.
That's a different day than Woden's Day.
Today is Friday's day.
Nobody?
I'm saying I'm still not over Thursday.
Like the hottest to coldest, the classification.
We can determine the temperature from those spectral lines. Which is why we call them the spectral classes. or spectral types, excuse me. We called it the spectral type because we get the temperature from looking at the spectra. Now we have one more thing. We actually determined the luminosity class, or from the spectral lines. How can we determine the luminosity class from the spectral lines? It comes down to being related to what Aldwin said. If you have a really big star, you of course have a whole lot of gravity, right? Which makes it so it really pulls a lot of mass in, makes it really have a lot of fusion going on in the center, which then results in a lot of outward push, and it actually makes the outward atmosphere very thin. So massive stars have thin atmospheres. If it's a thin atmosphere, then that means that the molecules don't collide with each other very much. When they collide, you end up having your spectral lines get fuzzed out. They become broader because of energy transferred in the collisions. So when you have a thin atmosphere, you don't have that broadening of the peaks, so you have narrow absorption peaks. So massive stars have narrow absorption peaks. Conversely, low mass stars have broad absorption peaks. Absorption, I spell it two different ways. So we can determine if it's a large star or a small star, or more importantly, it's actually large and small. I should have said not massive, but large. It's wonderful to be able to change your mistakes. Small stars have broad absorption peaks. So by looking at the size of that absorption peak, that's how they actually determine the luminosity class. So those are all things that we can get from those spectral lines. I spent 10 minutes on that. But we spent time learning about the spectral lines and how light is absorbed and produced, because you can see a lot of what we believe we know about stars comes back to those spectral lines. So I will, next class period, next week, talk about the life cycle of stars. So we're going to talk about how stars are formed, how they live their lives on the main sequence, and then how they die and become white dwarfs and get hot next class period. Here is a picture just illustrating the life cycle. So I'm going to leave you with this. You start with a gas cloud. Then you have it collapse to produce the protostar with a protoplanetary disk. Planets will form in that disk, and it becomes a star like our sun. When our sun dies, it will become a red giant. And then it will become a yellow giant. It'll be stable as a yellow giant for a while. And then it'll be a second red giant, and then it will maybe form a planetary nebula with a little white dwarf in the center. And then when that planetary nebula fades, all we'll have left is the white dwarf.
Is Polaris in that second stage? The second and the yellow giant stage?
I don't remember, so I won't answer. I don't know. All right, have a great weekend. I know there's no football games of any importance this week, so